Hey everybody. Today we begin a whole new topic in number theory. This is called congruences. And maybe I could have entitled this Congruences and Modulo Arithmetic. What we're about to study today is at the heart of coding theory, encryption. So that makes this an extremely hot topic in today's cyber world. Now, this goes back a few hundred years to a guy named Gauss. He's the first guy who, he's the first person that realized a clever way of adding up the sum of the first 100 natural numbers when he was like 5 years old or something. And we used something similar to that in a discussion we had about a week ago. It was a lemma to one of our proofs. Gauss is the person who founded the science of congruences. And at the surface, it doesn't really seem like this sort of thing would go very far. And yet, either he pursued it until the mine was tapped out, which it turned out it was a very fruitful mine to be mining, or maybe just because he was smarter than anybody else in his century, he knew right from the get-go where this was going. At any rate, when it comes to encryption, coding, encoding, and so forth, barcodes, any kind of security codes and so forth, these are at the heart of that. So let's get right into it, okay? Here's our definition. Let n greater than or equal to 2 be a natural number. N is a natural number and it can't be 1. N is greater than or equal to 2. Two integers a and b are congruent modulo n, denoted a is congruent to b modulo n, exactly, oh, and I hate it when I leave out a word. Thankfully, I had some space to insert it. Two integers a and b are congruent modulo n. A is congruent to b modulo n, exactly when a minus b equals kn for some integer k. So in other words, if the difference of a and b is a whole number multiple of n, then a and b are congruent modulo n. Otherwise, a and b are incongruent modulo n. And we denote it this way. A is not congruent to b modulo n. And typically, I won't read this by saying a and b are congruent modulo n. You heard what I said. I said a is congruent to b modulo n. That's typically what we say. And this remark bears that out. The expression a is congruent to b modulo n is also read a is congruent to b modulo n. So we can look at this statement right here and say a is congruent to b modulo n, or we can say a and b are congruent modulo n. We can read that either way. We look at this statement and we can read it as a is congruent to b modulo n, or we can read it as a and b are congruent modulo n. this expression, we can read this as A is not congruent to B modulo n. A is not congruent to B modulo n. Or A is incongruent to B modulo n. So we see this expression. A is incongruent to B modulo n. Or A is not congruent to B modulo n. We can also say A and B are incongruent modulo n. Different ways of saying the same thing. And there's one more thing that has to do with how we write things and how we say them. And I'll get to that in just a second. As far as the spoken word goes, oftentimes instead of saying modulo n, we say mod n. So if I see something like this, I can say A is congruent to B mod n, or A is congruent to B modulo n, same thing. Or A and B are congruent mod n, or A and B are congruent modulo n. That's just the terminology and the slang and so forth. And similarly, if we see something like this, we'd say A and B are incongruent mod n, or A and B are incongruent modulo n. Or we can say that A is not congruent to B modulo n, or A is not congruent to B mod n. Okay, we got all the lingo down now. Let's get to some math. Here's our first observation. Given a natural number n greater than or equal to 2 and an integer a, the division algorithm gives us a is equal to quotient times divisor plus a remainder. And here our divisor is n. So we're taking a and we're dividing it by n, an integer greater than or equal to 2. And a is equal to quotient times divisor plus remainder, where the remainder has to be greater than or equal to 0 and strictly less than n. I could write this as r is greater than or equal to 0 and less than or equal to n minus 1. Maybe that would be a better way of writing it. The remainder, you know what, I am going to write it that way. I'm just going to can this and just put n minus 1 here. So r can be anything between 0 and n minus 1 inclusive. So the possible values of r are 0, 1, 2, 3, dot, 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 n minus 1. And we have another observation. But before we go there, let's just recap this quickly. We have n, which is a natural number greater than or equal to 2. So in other words, n is a natural number that's not equal to 1. If we use n as a divisor, we get a equals quotient times n plus the remainder, where the remainder has to be strictly less than n. So r, the remainder, can be anything between 0 and n minus 1 inclusive. Okay? Next observation. Since a minus r is equal to qn, wait a minute, now how do we know that? Okay, we know that from up here. Yep, we just subtracted r from both sides. Subtract r from both sides, a minus r is equal to q times n. And you know what that means? The difference of a and r is a whole number multiple of n. And that means that a is congruent to r mod n for some r between 0 and n minus 1. Okay. A minus r is congruent. I'm sorry, this means that a is congruent to its remainder, modulo n. The difference of a and the remainder is a whole number multiple of n. So that means these two things are congruent mod n. A is congruent to its remainder mod n. That's an important observation. Now, A can be congruent to a lot of other things mod n, but specifically, A is congruent to its remainder when divided by n, modulo n. We're back again, and I'm going to give a definition, but before I do, let's backtrack a little bit. Remember, we had a natural number n greater than or equal to 2, and we were using n as a divisor to divide a. And the division algorithm gave us that a is equal to some quotient times n plus a remainder r. And remember, the division algorithm tells us that this quotient and this remainder are unique. So given a and the divisor n, there's only one remainder between 0 and n minus 1 that will work here. And when we rewrite this equation in this fashion and realize that what this equation is telling us is that a is congruent to r modulo n, there's only one natural number or one integer between 0 and n minus 1 that will work here. A is congruent to exactly one of these numbers between 0 and n minus 1. And the number between 0 and n minus 1 that a is congruent to is unique. So given a natural number, and n greater than or equal to 2, a is congruent to exactly one number between 0 and n minus 1. So this number that a is congruent to mod n, this r, where r is between 0 and n minus 1, this r is unique. There's only one number between 0 and n minus 1 that a can be congruent to modulo n. So this set of numbers from 0 to n minus 1 is kind of special, and we have a definition for them. Given n greater than or equal to 2, the set of integers from 0 to n minus 1 is called the set of least non-negative residues modulo n. Well, that's a fancy title. Just remember that when it comes to arithmetic modulo n, this set of remainders from 0 to n minus 1 is a very special set. And I will comment on that as soon as I erase some of the board. Bringing our previous thought to completion, here's the relevance. When we write A is congruent to R modulo n, we will choose the value of R such that R is between 0 and n minus 1, where n is the divisor. In other words, R is going to be that remainder that the division algorithm gives us. So when we write A is congruent to R mod n, R is going to be something between 0 and n minus 1, unless we have really good reason for doing otherwise. See, we could write this some other way, but we shouldn't unless we have a good reason. And sometimes we will have a good reason. But if we don't have a good reason for writing it in a way different than this, this is how we're going to write it. And let's just look at an example. Let's say here that A equals 25 and n equals, oh my goodness, let's say 7. Okay, so 25 is equal to 3 times 7 plus 4. And here's A, here's n, and here's our remainder. And so what we should say, unless we have good reason to do otherwise, what we should say is that 25 is congruent to R, which is 4, mod 7. Now, we don't have to say that, but we should write it this way unless we have a really good reason to do otherwise. Here's what we could do. We could say A is 25. Whoops. We could take A again and say that that's equal to 2 times 7 plus 11. And here's A, here's n, and here's the remainder, which is greater than the divisor, which is a no-no. Now, this statement is correct. It's just not the way we want to write it. And we could say, and we'd be telling the truth if we did, that 25 is congruent to 11 mod 7. This is correct, but not preferable unless we have a good reason for doing that. Similarly, we could say 25 is equal to 1 times 7 plus 11. And again, 25 is our A, and n is our divisor 7. And I lied here, didn't I? What do I want to say? Maybe 18? I think so. And we could write 25 is congruent to 18 modulo 7. And let's see, does it end here? No. So maybe what I should put here to let you know that this can go on indefinitely. We could have 25 is equal to 0 times 7 plus 25. Or we could have 25 as negative 1 times 7 plus 32, and so forth. Let's see. Forgive my ignorance. Not preferred. I think that's spelled correctly. These are not incorrect. This is correct, this is correct, but they're not kosher. We don't typically write it in this form or this form because here R, yeah, that's what I would do. Here's my R, here's R, here's N, here's R, here's N. Here's why they're not kosher. The remainder is greater than the divisor. The remainder is greater than the divisor. Now these statements are correct, but we don't typically write it in these forms because typically we don't want the remainder to be greater than the divisor. This statement is correct, but it ain't kosher. This statement is correct, but it ain't kosher. Typically, we're going to write it this way because here's our remainder, and here's our divisor, and the remainder is strictly less than the divisor. So this is the preferred form, unless we have a really good reason. And I might illustrate it this way. When we're coming to an intersection and the light is red, we stop. Unless we have a really good reason not to. If we have somebody in the car that may be dying of a gunshot wound and we got to get them to the hospital, we're not going to stop at the red light, and that's acceptable. Life, it's a matter of life and death, and we go right through that red light. But if we don't have a good reason not to stop at the red light, we do it. That's correct and that's preferable. The same thing here. This is not preferred, but there may be an occasion where we might want to write this, or we might see this. This is correct, but not preferred, but there may be an occasion where we would benefit by writing the relationship this way. So, we write it this way unless we have a really good reason to do otherwise. And that's what that bit about the set of least non-negative residues was about. They gave that set of numbers from 0 to n minus 1 a name, because unless we have a good reason to do otherwise, a modulo n is going to be equal to one of those numbers between 0 and n minus 1. Now here's our first big result, and I say big because Even though it's very easy to grasp, we're going to use this quite a bit. And we're going to recall the definition of congruence modulo n. Given n a natural number greater than or equal to 2 and some integer a is congruent to b mod n exactly when the difference of a and b is a whole number multiple of n. In other words, a minus b is equal to kn, where k is a whole number. That's our definition of congruence modulo n. A and b are congruent modulo n exactly when their difference is a whole number multiple of n. And if that's not true, then they're incongruent modulo n. Well, we have our first theorem, and this is an equivalent characterization of congruence modulo n. So this is an equivalent or alternative characterization of congruence modulo n. Given integers a and b, and n greater than or equal to 2, a is congruent to b mod n if and only if a and b have the same remainder using the division algorithm when divided by n. Okay, so let's compare this and this. The definition says that a and b are congruent modulo n if their difference is a whole number multiple of n. And that's exactly the same thing as saying that a and b are going to have the same remainder according to the division algorithm when divided by n. And it goes the other way. If a and b have the same remainder when divided by n using the division algorithm, that means that a and b are congruent modulo n. So this is often a convenient characterization to use if we're doing proofs involving modulo arithmetic. We can either use the fact that the difference of a and b is a whole number multiple of n, or we can use the fact that a and b are going to have the same remainder when divided by n. And to make this complete, I guess I'm also going to have to put this statement down here. If a and b don't have the same remainder when divided by n, then they're incongruent. So a and b are congruent modulo n exactly when a and b have the same remainder when we apply the division algorithm and we're dividing by n. If we divide a and b by n and they have different remainders, then a is not congruent to b modulo n. And this is actually a pretty easy thing to prove, so we're going to do it. It's proof time. Given integers a and b and natural number n greater than or equal to 2, a is congruent to b mod n if and only if a and b have the same remainder using the division algorithm when divided by n. This is an if and only if proof, so we have to prove it both ways. So let's let our hypotheses be given. Let a and b be integers, and let n be a natural number greater than or equal to 2. We're going to prove that if a and b have the same remainder when divided by n, then a is congruent to b mod n. And so this essentially is our hypothesis for this direction of the proof. So we'll let the hypothesis be given. Suppose that A and B have the same remainder when divided by n. Okay. And this implies that A is equal to case of 1n plus r, and B is equal to case of 2n plus r, where k1 and k2 are both integers. Okay. Now, how are we going to prove that A is congruent to B modulo n using all that we have right now, which is the definition? The definition says that A is congruent to B mod n. What was the definition again? If their difference is a whole number multiple of n. So let's look at the difference. A minus B is equal to k1n plus r minus k2n plus r minus r is 0, so we have k1n minus k2n. N is a common factor, so we have k1 minus k2. Well, by our hypothesis, k1 and k2 are both integers. So k1 minus k2 is the difference of integers, so that's an integer. k1 minus k2 is an integer. So the difference of A and B is a whole number multiple of n. This implies that A is congruent to B mod n. So we just finished the proof in one direction. Now we got to do the other direction. We have to prove that if A is congruent to B mod n, then A and B have the same remainder using the division algorithm when divided by n. So let's do a turnabout and prove it in the other direction. Okay, let's prove this son of a gun going the other way. Here's our hypothesis. A is congruent to B modulo n by the hypothesis. And we're going to show that this means that A and B have the same remainder when divided by n. So the first thing I'll do is say, let the hypothesis be given. Let the hypothesis be given. Suppose that A is congruent to B modulo n. And when there is a hypothesis, or when there are hypotheses, why do I usually start out saying let the hypotheses be given? Usually it's a stalling tactic on my part. I have no idea how I'm going to do the proof. So I might as well just start with what I'm given and maybe write out what it means. Let's see. A is congruent to B modulo n. What does that mean? The only thing that we have to go on right now is our definition, which says that two integers are congruent modulo n exactly when their difference is a whole number multiple of n. Okay. So this implies by the definition, which is all we have to go on right now, this implies that A minus B is equal to some integer times n. Okay. So that's what our hypothesis means. I don't know what else to do right now, so I'm just going to poke and prod. The division algorithm applies to all integers, including A and B. So what I'm going to do is I'm going to apply the division algorithm to B. It may yield something fruitful, it may not. If it doesn't, I can just stop and go in another direction. It doesn't mean I did anything wrong. It just means that maybe it was a good idea that didn't pan out. I don't know what to do, but I'm either going to take A or B and apply the division algorithm to it, because I can't think of anything else to do. Just randomly, I'm going to apply it to B. So B is equal to a quotient that I'll call K2 because I've already used K1. B is equal to a quotient times n plus a remainder, where R is between 0 and n minus 1. Oh my goodness, I think I know where this is going. I think I know where this is going. I'm going to look back up here. Okay. Maybe I know where I'm going. Let's see, A minus B. maybe I'll do that. A equals B plus, what is it, K1N. Okay. Yeah, okay, yep, that's exactly what I wanted to do. And where did I get this thing? I got it from here. I just moved B to the other side. So A equals B plus K1N. And what is B? It's K2N plus R. So that's K2N plus R. That's B. Plus K1N. And I'll reorganize things a little bit. And we look at this term, and son of a gun, it's got a common factor of R. Now remember, K1 is an integer. K2 is an integer. So K1 plus K2 is going to be an integer. So what have we established? A is equal to K2 plus K1 times N plus R, where this K1 plus K2 is an integer. Okay. And notice, this is the same R that, my goodness. This is the same R that we got when we applied the division algorithm to B. So R is between 0 and N minus 1 inclusive. And this is, if we've been keeping track of things, the same R. And this is what we were intending to prove. Aha, so we did it. Now, what this is an alternative characterization of congruence modulo n. And depending how this topic of congruence is introduced, we can use the definition of congruent modulo n as being the difference of two numbers is a whole number multiple of n. Or we can start off using as the definition of congruence modulo n that each one has the same remainder when divided by n. But we're going to wind up at the same spot eventually. In other words, this characterization of congruence modulo n and this characterization of congruence modulo n are equivalent. And from here on out, we can use either one of those, either to show that two things are congruent modulo n, or we can assume either one of these things if we already know that two integers are congruent modulo n. They're both equivalent, and we use whichever characterization is most convenient for us to use from here on out. Here's our theorem that gives us all the fundamental properties of congruences, modulo arithmetic. And here are the premises or the hypotheses. N is a natural number greater than or equal to 2. A, B, C, D are integers, any integers. And K is any positive natural number. Now, we're not going to see K until this last property, but this last property is probably the truly amazing thing about congruences. Let's go through these things one by one. A is congruent to itself modulo n. Well, okay. And by the way, a lot of these properties of congruences have analogs when it comes to equations. Equations, A is equal to itself, reflexive property. Same thing holds for congruences. Every integer is congruent to itself. Secondly, if A is congruent to B and B is congruent, if A is congruent to B, then B is congruent to A. The symmetric property, just like if A is equal to B, then B is equal to A. If A is congruent to B mod n and B is congruent to C mod n, what do you think is going to happen? Yep, A is going to be congruent to C mod n, the transitive property. A congruent to B, B congruent to C, then A is congruent to C. Now this is kind of interesting. We have two congruences. A is congruent to B, and C is congruent to D. And there are two things that can happen. We can add congruent things to both sides of the congruence. Well, where have we seen something like that before? We can take two equations and add them together, right? We can add the left sides together and the right sides together, and we still have an equation. The same thing holds for congruences. We can add congruences. Take the left side, A, C, add them together. Take the right side, B, D, add them together. We still have a congruence. And that holds not just for addition, but for multiplication as well. Take the left sides, A and C, multiply them together. Take the right sides, B and D, multiply them together. And we still do have a congruence. So the things that we can do with equations, by and large, we can do with congruences. Just like we can add two equations, and we'll do that if we have a system of two equations and two variables and we're doing elimination. We'll add one to the other, right? We can do the same kind of thing with congruences. And we can multiply both sides of a congruence. by congruent things, and we still have a congruence. Now 5 is a no-brainer. 5 is really a special case of 4. If A is congruent to B, then A plus C is congruent to B plus C. A times C is congruent to B times C. Now with equations, we can add the same number to both sides and we have an equation. Still have an equation. Or we can multiply both sides of an equation by the same non-zero number. We still have an equation. This is actually, though, a special case of number 4, where C and D happen to be equal. And of course, every integer is congruent to itself. So if we just say that C and D are congruent, we get step 5. A plus B is congruent to B plus C. A times C is congruent to B times C. Now the last of these properties, in my opinion, is the one that's really mind-blowing. We can raise both sides of a congruence and still have a congruence. And algebraically, a congruence, let's see, two things are congruents if their difference is a multiple of n, a whole number multiple of n, or two things are congruent if when we divide them by n they have the same remainder. It's not obvious that that would continue to hold if we take both sides of a congruence and raise them to the power of a positive whole number. And remember what k is. K is a natural number, 1, 2, 3, 4, 5. So we can take both sides of a congruence and raise them to the power of any natural number, and the congruence is preserved. And this is by far the most powerful and far-reaching property of congruences, in my opinion. This is where the real power of congruences and modulo arithmetic lies. Now, I guess we can take a look at a few of these things and just convince ourselves that, yeah, they're all true. We'll look at each of these properties one by one and see why they're true. Some of them are no-brainers, but it's beneficial for us to work through them because it will give us a little bit of practice working with the definitions of congruence and so forth. For any integer A is congruent to itself mod n. Well, let's see. When are two numbers congruent modulo n? When their difference is a whole number multiple of n. Does that happen here? A minus A is equal to 0, which is equal to 0 times n. The difference is equal to a whole number multiple, an integer multiple of n. So A is congruent to A mod n. Their difference is an integer multiple of n, so they're congruent mod n. Okay, let's do the next one. If A is congruent to B mod n, then B is congruent to A mod n. Here's our hypothesis. So we'll let the hypothesis be given. we suppose that A is congruent to B mod n. Well, what does that mean? By the definition, the difference of these two numbers is equal to some integer k times n. Now I'm just going to multiply both sides by -1. The difference of b minus a is equal to -kn, but since k is an integer, -k is also an integer. So that means that b is congruent to a mod n. Let's see, what was the next one? Transitive, okay. Next, if A is congruent to B mod n and B is congruent to C mod n, then A is congruent to C mod n. So here's our hypothesis. A is congruent to B mod n, and B is congruent to C mod n. Well, what does that mean? By definition, this means that their difference is some whole number multiple of n, and this means that their difference is equal to some whole number multiple of n, and I think I know how this is going to work out. I haven't really thought it out, but I think I can see how it works. We're trying to prove something about A and C. We want to show that A minus C is a whole number multiple of n, because that will mean that A and C are congruent modulo n. And I think we have it. A minus C is going to be A minus B plus B minus C. The B's cancel each other out. We just have A minus C. But A minus B is K1n. and b minus c is k2n. K1's an integer, K2's an integer, so K1 plus K2 is an integer. So we'll just recap our result here. A minus C is equal to K1 plus K2n. Where K1 plus K2 is an integer. So in other words, A minus C is a whole number multiple of n. Yay! Okay. And oh, by the way, that was number 3, wasn't it? If A is congruent to B and B is congruent to C, then A is congruent to C. 4A, let's go for it. If A is congruent to B mod n and C is congruent to D mod n, then A plus C congruent to B plus D mod n. And here is our hypothesis. So let's get this proof going. And again, I'm writing out the hypotheses because I'm a coward. I have absolutely no idea how I'm going to do this, and I'm stalling and hoping that I'll get some sort of inspiration while I stall. But I'm also doing it because it's a good mathematical practice. Write out the hypotheses and in the process maybe even explore some of the consequences of the hypotheses. But I am stalling. I have no idea how I'm going to do this. Okay. Let's see. A congruent to B mod n. What does that tell us? That their difference is a whole number multiple of n. So that means that A minus B is equal to some integer, K1, times n. Now I'll have to do the same thing with this part of the hypothesis. C congruent to D mod n tells us that the difference of these two things is a whole number multiple of n. So C minus D is equal to some integer, I'll call it K2 because I don't have much of an imagination. Some integer K2 times n. Okay. Now, you know what? I just got a flash of inspiration. And I haven't done anything wrong, but I think I'd like to insert something between here and here. Okay. So this implies, let's see, what did I want to say now? I wanted to say that this means that A equals B plus some integer k plus 1n. Okay, and what I just erased, I can now rewrite C congruent to D mod n means that their difference, C minus D, is equal to some integer k2. Yeah, my imagination hasn't improved since I wrote this the last time. For some integer k2. And a consequence of this is that C equals D plus k2n. Okay. And, oh, I see things falling into place. I'm trying to show that A plus B is congruent to B plus D. Okay? So let me find out something about A plus C. A plus C, based on what I have written here, is equal to B plus K1n there's our A, and C is D plus K2n. And that is equal to B plus D plus K1n plus K2n. Oh yeah. And that's equal to B plus D, common factor of n here, so we're going to have K1 plus K2n. K1, integer, K2, integer. So their sum is also an integer. So what we established is that A plus C is equal to B plus D plus K1 plus K2n. And what did we really want to find out? We wanted to find out the relationship between AC and BD. We wanted to show that A plus C is congruent to B plus D. And one way we can do that is to show that their difference is a whole number multiple of n. Okay, let's look at their distance, their difference. A plus C minus B plus D is equal to, there we are, K1 plus K2n. And we already ascertained that K1 plus K2 is an integer. Okay, I'm going to erase a little bit of the board. AC minus BD is some integer times n, so I'll just, for reinforcement, acknowledge that K1 plus K2 is an integer. But which is all I have to show. A plus C minus B plus D is a whole number multiple of n. So that means that A plus C is congruent to B plus D mod n, which is what I needed to show. Okay, now that was 4A. I should do 4B also, I think. Okay, 4B. I don't know if this is the best way to do it, the way I'm going to do it, but it's the first thing that popped into my mind. So this is what I'm going to do. And essentially, I'm going to repeat the procedure that I followed to do everything that came before this. A is congruent to B mod n, and C is congruent to D mod n. That AC is congruent to BD mod n. In other words, we can take two congruences and multiply the left sides and multiply the right sides, and we still have a congruence. And we'll acknowledge our hypothesis or maybe in this case I should say hypotheses. Okay, we've supposed our hypotheses, and what do we know? A congruent to B mod n implies that their difference is a whole number multiple of n. A minus B is equal to K1n for some integer K1. And I'll do the same thing with C congruent to D. C congruent to D implies their difference, C minus D. Oh, you know what? I'm about to do something that I did in the last proof and I regretted it. This is not wrong, but let me delay this just one step. You know, you can't teach an old dog new tricks, and I guess that's why I didn't learn from the last proof. What I want to do is take this thing and rewrite it. A is equal to B plus K1n. I'm pretty sure that's what I want to do. Now, I'll look at this congruence. C congruent to D mod n tells us that their difference is a whole number multiple of n. So C minus D is equal to K2n for some integer k2. And I'll draw a similar conclusion from this, namely that C is equal to D plus K2n. Oh my goodness. After 4a, this should have been a no-brainer. And, I started to not rewrite this when I had the opportunity. Okay. Now, what are we trying to show? AC is congruent to BD. In other words, the difference of AC and BD is a whole number multiple of n. So I think it's a good time to introduce the word observe. AC is equal to, let's say, A is equal to B plus K1n, and C is equal to D plus K2n. And I'll just multiply this out. Let's see. I get BD plus, let's see, B times K2n plus K1n times D. I'll write that as D K1n. And K1n, K2n, I'll write that as K1, K2n squared. Okay. And all of these terms except the first have at least one factor of n. So I'm going to factor that n out, and I'll get bk2 plus dk1 plus k1, k2n times n. And what do we know about b? It's an integer. K2 is an integer. D is an integer. K1 is an integer. K1 times K2 is going to be an integer. N's an integer. So this is the sum of products of integers. Products of integers are integers, and sums of integers are integers. So this is going to be an integer. Okay. So we have AC is equal to BD plus this garbage. You know what? I'm going to call this whole thing M. And just say that AC is equal to BD plus MN, where M is an integer. So, okay, I'm not done yet. I thought I was, but I'm not. I'm this far from being done. What do I have to do? To show that AC is congruent to BD, I have to show that their difference is a whole number multiple of n. So all I have to do is say AC minus BD is equal to MN, where M is an integer. And that means AC is congruent easier way to do this? Perhaps. I really didn't spend any time thinking of an alternative way. I just wanted to use the definitions and the theorems to do these. And might not be a bad idea for us to work through some of these, just to gain some facility applying the definition and the theorem. And when I say definition and theorem, the one theorem that we had before, 1, 2, 3, 4, 5, 6, the one theorem that we had was the theorem that was an equivalent characterization of congruence modulo n. It's an equivalent characterization. It's equivalent to the definition, so really we can use either one of those as definitions from now on. Okay, next. I'm not going to do number 5 because, as I mentioned earlier, number 5 is just a special case of number 4 where C and D happen to be equal, or maybe I should say number 5 is a special case of number 4 where D equals C. So there's really nothing to prove there for number 5. Number 6, I thought about how the heck I was going to do this, because I had absolutely no idea. This has been one of those facts that's just always amazed me about modulo arithmetic and congruences. And I thought, how on earth am I going to do this? I don't know. And for some reason or other, I thought, how would my students go about doing this? And maybe that was a good thing for me to think of, because a lot of you, and perhaps all of you, have been doing very good work. And you've had some very good ideas. And I thought, okay, how would my students do this? And immediately I thought, binomial theorem. Now, I don't know if that's the way the author does this, but I feel comfortable going this route. I can see how it works from beginning to end, even though I haven't worked it out. This is one of those few proofs where I see it clearly from beginning to end. So I'm going to do it the way that I think my students would do it. And let's see, here's our hypothesis. Okay. Let the hypothesis be given so we suppose that A is congruent to B mod n. Okay. And what does that tell me? It tells me that the difference of A and B is equal to a whole number multiple of n, and I'll call this m because we've already used k, and using the binomial theorem, I'm going to use I, so m is available. So A minus B is a whole number multiple of n, and that means that A is equal to B plus mn, where m is an integer. Okay. A to the k is equal to B to the k. I'm sorry, That's what I'm trying to show. But A is equal to B plus Mn. So A to the K is equal to B plus Mn to the K. And this is where the binomial theorem comes in. We're going to get sum from I equals 0 to K of K choose I. And that's going to be B to the K minus I times M times N to the I. Okay. Holy moly. And let's see what we got. Yeah. When I is 0, we have K choose 0, B to the K, Mn to the 0. When I is 1, we have K choose 1, B to the K minus 1, Mn to the first. Okay, do I have room for 3 more terms? Maybe. When I is 2, I have K choose 2, B to the K minus 2, Mn squared plus dot dot dot. When I is equal to K minus 1, I have K choose K minus 1, B to the first, Mn to the K minus 1. And the last term, K choose K, B to the 0, Mn to the K. This term is just going to be B to the K. K choose 0 is 1. M times M to the 0 is 1. This term is just B to the K. This will be K, B to the K minus 1 times M times N. I'm sorry. K, B to the K minus 1, M times N. And this, I'll just leave this as K choose 2. B to the K plus B to the K minus 2, Mn squared plus dot dot dot. K choose K plus 1 is just K. B to the first, M times N to the K minus 1. And this one is just 1 times 1 times Mn to the K. I'm going to do something like that on the next term. I have k choose 2, which is some integer, b to the k minus 2 times m squared n. But I'm going to factor out that other factor of n and put it right here. And then over here, I have k, b, m to the k minus 1, n to the k minus 1, but I'm going to take one of those factors and put it out here. So what I'm going to have is n to the k minus 2. And then here I'm going to have m to the k, n to the k minus 1 times n. Oh, shoot. Okay. Now guess where I'm going with this. All of these terms have at least one factor of n. And in each of these terms, the contents are integers. So this whole thing is just some integer and I got to call it something. I can't call it m, I can't call it n, I can't call it k, I can't call it I can't call it a, I can't call it b. My goodness. I'm going to call it p, integer p. So let's see, what do we have? We have a to the k equal this thing. Some integer p times n. That's what we got. And I subtract b to the k from both sides. That is, a to the k minus b to the k is some whole number, some integer multiple of n. Well, let's see. If these two things differ by a whole number multiple of n, then they're congruent modulo n. And that concludes our proof. And I wasn't kidding with what I said earlier. If I had to do this proof a month ago, I don't think this approach would have occurred to me. But I've seen your work in the homework and on the tests, and it's very good. And I know at least some of you, maybe all of you, would have opted for this way, something that I wouldn't have thought of. But we've proved all of the fundamental arithmetic and algebraic properties of congruences. Let me see if there's something else that I need to mention right now. Okay, I think we'll finish off with a typical modulo arithmetic / congruence exercise. Compute 10 raised to the 1024 mod 23 without using a computer or a calculator. Our strategy is going to be to find a power of 10 that is congruent to a small number mod 23. And that small number can be positive or negative. Ideally, we'd like to find a power of 10 that's congruent to 1 mod 23. If we find something that's congruent to 2 mod 23, that's pretty good. Or negative 1 mod 23, that's pretty good also. But for reasons that may become obvious as we progress through this exercise, our strategy is to find powers of 10 congruent to a small number, positive or negative, modulo 23. And if we get negative 1 or positive 1, we've hit the Holy Grail, okay? So let's see what we can do. 10 is congruent to negative 13 mod 23. Well, how do we know that? Their difference, 10 minus the negative 23, is equal to 23, which is a whole number multiple of 23. So the difference of these two is a whole number multiple of 23, therefore they're congruent mod 23. Okay, what about 10 squared? Well, let's see. 10 squared is 100. And let's see. A 100's just a little bit bigger than 92. And 100 minus 92 is 8. Now, let me go over that again. 100 minus 92 is 8. Or I could say 100 minus 8 is 92, which is a multiple of 13. So 10 squared, 100, minus 8 is equal to 92, and 92 is what, 4 times 23? Okay. Now, there was another way I could have arrived at this. Alternatively, I could have said this. 10 squared is congruent to negative 13 squared mod 23. Because 10 is congruent to negative 13, 10 squared is congruent to negative 13 squared. And negative 13 is squared is 169. And let's see, 169, that's 8 greater than 161. So 169 minus 8 is 161. And this 161 is a multiple of 23. And I'm not sure if I mentioned that when I started out. But for our reference, I looked at all of the fairly small multiples of 23. Uh, 169 minus 8, the difference of these two things is equal to 161, and let's see, what is that? 5, 6, 7, this is 7 times 13. So the difference of 169 and 8 is a whole number multiple of 13, so 169 and 8 are congruent mod 13, mod 23. I'm sorry, 7 times 23 here. 161 is 7 times 23. The difference of 169 and 8 is a whole number multiple of 23. So 169 and 8 are congruent mod 23. Okay. Let's see. 10 cubed. Let's see. 10 cubed, that's equal to 10 squared times 10. And 10 squared is 8 mod 23. And 10 is, oh my goodness, what is 10? 10 is 11 mod 23. No, it's not. 13 mod. Okay. Oh, I got it. 10 is congruent to itself mod 23. That's the best way of doing it. And 8 mod 23 times 10 mod 23 is 80 mod 23. And 80 is 11 greater than 69. So 80 is congruent to 11 mod 23. And again, our reasoning is 80 minus 11 is 69, and that's equal to 3 times 23. So 80 and 11 are congruent mod 23 because their difference is a whole number multiple of 23. Well, I sure hope we hit the Holy Grail soon. 10 to the 4th. Come on. Let's see, 10 to the 4th. That's congruent to 10 squared times 10 squared mod 23. Apparently that's what I want to do. No? Let's try 10 cubed times 10 mod 23. 10 cubed, just for consistency's sake, let me do this. 10 cubed mod 23 times 10 mod 23. And 10 cubed we found out was congruent to 11. and that's 110 mod 23. 110 is 18 greater than 92. So 110 minus 18 is 92, which is a whole number multiple of 23. Mod 23. Or I could do this. 110 is 5 less than 115. So I could say that 110 is congruent to negative 5 mod 23. Whoops. Now, why is 110 congruent to negative 5 mod 23? Because 110 minus negative 5 is 115, and that's a whole number multiple of 23. So 110 minus a negative 5 is equal to 115, which is 5 times 23. I'm running out of board space, so let me just write down what we've established so far. Ten is congruent to negative 13 mod 23. 10 squared is congruent to 8 mod 23. 10 cubed is congruent to blah, 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 blah. Congruent to 11 mod 23. 10 to the 4th is congruent to negative 5 mod 23. And we said that was congruent to 18 mod 23. Okay. Let me get rid of all of this garbage. We definitely have not found a power of 10 that is equal to a small number, mod 23. Hopefully we can. And I'm tired of going in increments of 1 when it comes to the exponents. So instead of doing 10 to the 5th and 10 to the 6th, I'm going to try 10 to the 8th. This is equal to 10 to the, or it's equal to 10 to the 4th squared. And that's congruent. Let's see, what is 10 to the 4th? Negative 5 mod 23. So 10 to the 4th is congruent to negative 5. 10 to the 4th squared is negative 5 squared mod 23. And that's 25 mod 23. And that's congruent to 2 mod 23. Now, why do I say that? 25 minus 2 is equal to 23. The difference of 25 and 2 is a whole number multiple of 23, so they're congruent mod 23. Okay, okay. And you know what? I'm going to rewrite the result here. 10 to the 8th is congruent to 2 mod 23. Now here's where I'm going with this. I have something that gives me 11 mod 23 and something that gives me 2 mod 23. 11 times 2 is 22, which is 1 less than 23. 11 times 2 is equal to 22, and that's equal to negative 1 mod 23. A small number mod 23. So here's what I'm going to do. I'm going to take 10 to the 8th times 10 cubed, and that's going to be congruent to 11 mod 23 times 2 mod 23. 11 times 2 is 22 mod 23. And I claim that that's congruent to negative 1 mod 23. Now, why is 22 congruent to negative 1 mod 23? Minus negative 1, 22 minus negative 1 is 23. The difference of 22 and negative 1 is a whole number multiple of 23. So 22 and negative 1 are congruent mod 23. We found out something really important. What is 10 to the 8th times 10 cubed? It's 10 to the 11th, right? 10 to the 11th is congruent to negative 1 mod 23. We're almost there. If I get something that gives me 1 mod 23, I'll have this thing whipped. Well, how do I get 1 from negative 1? Just square negative 1, right? Okay. So that means that 10 to the 11th squared is congruent to negative 1 squared mod 23, and that's congruent to 1 mod 23. You know what? I think I got as much as I need. I think I do. I'm going to write down this added information. Let's see, 10 to the 8th. What was that? That was congruent to 2 mod 23. 10 to the 11th was congruent to negative 1 mod 23. And 10 to the 11th squared, that's 10 to the 22nd, is congruent to 1 mod 23. everything from here up and erase everything from here down. Remember, here's our goal. Compute 10 to the power of 1024 mod 23. And this is a number, oh my goodness, equal to the number of atoms in the known universe raised to the 100th power or something. Huge number. But I know that 10 to the 22nd is 1. So you know what I'm going to do? I'm going to express this exponent, 10 to the 24th, in terms of 22. Holy moly. Let's see. 10, 24, 22 goes in 4 times. Hopefully I did that right. Okay. $22 goes into 144 6 times, maybe? I'm guessing. Okay. $10 to the 24th, I'm sorry, 1024 is equal to 46 times 22 plus a remainder of 12. Okay. And that tells us that 10 to the 1024 is equal to 10 to the 46 times 22 plus 12. We have 10 raised to the sum of 2 exponents. So that'll be 10 to the power of the first term times 10 to the power of the second term. Let's see, is this right? We have 10 raised to a power, the whole thing raised to a power. So that's 10 raised to the product of those 2 powers. That's right. Okay. And we're not going to get this in terms of 10 to the 22nd, but we can get this in terms of 10 to the 11th. Ten to the 12th is 10 to the 11th times 10. Okay. Ten to the 22nd is congruent to 1 mod 23. 10 to the 11th is congruent to negative 1 mod 23. So let's see. 1 to the 46th is just 1. Negative 1 times 10 is negative 10. And if I want a positive number, I can add 23. Now, why is negative 10 congruent to 13? Because their difference, 13 minus negative 10, is equal to 23. That is 13 minus a negative 10. Their difference is a whole number multiple of 23. So negative 10 mod 23 is congruent to 13 mod 23. And this is a number between 0 and the divisor 23. This is as good as we can get. Okay? Final answer. 10 to the power of 1024 is congruent to 13 mod 23. See, I may or may not give another video before we do our homework. I'll sleep on it tonight.